start your lecture because everyone in the world is going to see your lecture today.
Are you recording it?
No, so it will be streamed by YouTube.
Oh, okay. Yeah.
And then at the end, you will let me know if it will be there forever, or I can just download it and erase it from YouTube.
Oh, okay. So I have to be more careful then.
No, by no means. So before you start, Lauren, so you already introduced yourself. How are you doing?
Oh, yeah, I'm fine. Yeah.
Great.
Doing good. Yeah.
Now, as I already told you, so some of the students of the class are here.
Yeah.
And some other sophomore students also are here.
Yes.
Like Pedro is also a sophomore. You see Moises is a senior. So next year he's going to New Mexico State University for a PhD in math. And then also on the video, you see Salvador.
Yes.
Student of the class.
Yeah.
Next year, he will be a senior here.
Hey, why don't you guys turn on your video so that I can see who you are?
There are many more somewhere there.
I see.
Oh, well, there is Daniel, but by some reason his name is Jose, but Daniel is also a senior. He's going to Notre Dame University next fall.
Oh, that's really wonderful. Hi, Daniel.
Hi.
Yeah.
And there's the other few fellows, Francisco and Pedro. They are second-year students.
I see. Oh, well, but does everybody know about differential forms?
Then I'm very sure that you will do a good job.
Well, okay, so
wait, now before you start, Lauren, so please say something about, because I have this one here.
Yes. Yes, that's a book I wrote with Raoul Bott. Yes. Yeah, that's a book which Andres contributed to by reading it and finding a lot of mistakes. Yeah. Yes, okay.
This is the one that we are using. We're following this one. Of course, I'm missing one, so sorry for that.
I see you're missing the one on differential geometry. Yeah.
But if you, before starting the talk, would you like to say something about what is the idea behind all of those books, or any anecdote that you would like to share for the students?
Oh, yeah. So the first book I wrote was Differential Forms in Algebraic Topology. And that was because my teacher at the time, Raoul Bott, taught a course, and he asked me if I wanted to turn it into a book. And I said, oh, sure, And so then I spent the next few years working on that book with him. Now, he said that it's not a good idea for two people each to write parts of the book, because then it would be, maybe inconsistent. The style might be inconsistent, the notation might be inconsistent. So he wanted me to write the whole book, but I would discuss with him, like what's in it, and he would read it, but he's this wonderful mathematician who cares about big ideas. And so he didn't always read very carefully. And yeah, when the book came out, there were actually a lot of mistakes. And I very quickly had to make a second printing, because I didn't have time to make a second edition. You know, Springer is a very honest publisher, so they didn't want to produce a second edition unless there were like at least 20% new material. But all I wanted to do was just to correct the mistakes. And so I did that. And so there was a second printing and then a third printing. And so if you get the book, you should get the third printing, because that's the one where all the mistakes have been corrected. Yeah, and then I decided that, you know, like, well, this book might be too hard. So why don't I write a couple of books to make it easier for students to reach that book? Yeah. And that's why I wrote the books on manifolds and differential geometry. Yeah. And then equivariant cohomology is really the algebraic topology of spaces with symmetry. So that's the most advanced book. Okay, so I want to talk about applications of differential forms. Oh, no. Why is it? No, I can't write.
Right, yeah, we have the blank.
Oh, but I could write earlier. Why?
Right.
Oh, maybe I have to click on this. Oh, yes.
Yes, we have it.
Yeah. So applications of differential forms to electricity and magnetism. Now, for those of you who don't know what differential forms are, they are basically just the dx dy that you see in calculus. So dx dy, or you can multiply them together, dx wedge dy. In calculus, you don't write that wedge symbol, but we do it here, okay? And in calculus, it's just a notation, but they actually can be given meanings so that they are independent objects. And they're really wonderful because they simplify vector calculus. So that's what I want to show you today. Like normally in the 19th century, Maxwell's equations are written using vectors. Okay, so I want to show you like how you can write them using differential forms. Now, the great disadvantage of writing equations in vectors, particularly Maxwell's equations, is that they make sense only in R3. Okay, so Maxwell's equations are four equations that describe electricity and magnetism. And there are various forms. I'm not going to write the most general form because, you know, it's more complicated. So let's just assume that space is empty. Okay, so it's a vacuum. Except that you have a charge, and a charge, an electric charge will produce a force, right? Like if you have another charge, which is, let's say you have two positive charges, they will repel each other, right? So there's a force there. An electric charge can produce a force, and the electric field is just force divided by charge. Okay, so an electric field is electric force per unit charge. So it is force divided by charge. You know, that's the electric field. Mm-hmm. And then the magnetic field, that's when you have a moving charge, so a current, and it's experimentally observed in the 19th century that when you have a moving charge, it produces a magnetic field, okay? And that's how, you know, these induction ovens work, right? You know, the electric current produces a magnetic field. So there's a magnetic force, and it makes the, you know, the atoms in your pot move around. And when they move around, they generate heat, right? And that's how you heat up a pot. So electricity and magnetism have a lot of applications, and then B is the magnetic field. Okay. And Maxwell's equations says that the curl of E is minus the time derivative of the magnetic field, and the divergence of E is 0, and then the curl of the magnetic field, this is curl from vector calculus, and del dot is the divergence. Okay, that's all from vector calculus. So the curl of the magnetic field is the time derivative of the electric field, and then the divergence of the magnetic field is 0. Okay, so these four equations are called Maxwell's equations, and they describe electricity and magnetism completely. Okay? But there's a big disadvantage to this formulation of Maxwell's equations in terms of vectors. Okay? And that's because the cross product is defined only on R3, right? And so these equations only make sense on R3, okay? And that's a problem because, you know, the universe might not be R3. So these equations make sense only in R3. But our universe may not be R3. Okay. In fact, the physicists, they have various models for the universe. It might be 9-dimensional, or 26-dimensional. I don't know. And these equations will not generalize, okay? And so the advantage of writing it in differential forms is that then it will make sense in any dimension and for any space, not just R3, okay? Oh gosh, so let's see. It seems that I would have to erase everything, right? Yeah. It's not like I can move pages around. So, oh God, and I don't know if there's a better way to erase. This is the first time I'm writing on whiteboards. I used to be able to write on my Notability in iPad. Okay. 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 Yeah. Good. Okay. So there's a correspondence between vectors and differential forms. Like if you have a vector, okay, in R3, and it's got three components, A1, A2, A3, then you can send it to one form, A1 dx plus A2 dy plus A3 dz, okay? But you can also send it to a two form. So you can send it to A1 dy wedge dz plus A2 dz wedge dx plus A3 dx wedge dy. Right? And a function it corresponds to a zero form. Actually, a zero form is just a function. All right, so I'm not doing anything there. But it can also correspond to a three form. So a three form would be f dx wedge dy wedge dz. Okay? Yeah. So you've got this correspondence between functions in differential forms. And then in vector calculus, you have three operations: the gradient, the curl, and the divergence. Okay. So the gradient of a function, it gives you the three partials, and that is actually the definition of df. Okay? And the curl of a vector field, okay, corresponds to the exterior derivative of, let me see. So let's call this form corresponding to V, omega V, and then it's a one form. I'll put a one there, okay? But a vector field can also give you a two form, and that I will call omega V with a two for two form, okay? Now the curl of the vector field is another vector field. So it goes from a one form to a two form. And so it corresponds to the V omega one. Okay? It corresponds to D of this one form. And that becomes a two form. So a two form also is a vector field. Okay. D increases the degree of the form by one. Now the divergence corresponds to D of the 2 form of V, and D of the 2 form is a 3 form, and the 3 form corresponds to a function. Okay, so the divergence of the vector field is a function. There's this dictionary between vector fields and differential forms. Okay? The problem here is that it's not quite one-to-one because a vector field can be a 1 form of a 2 form. Okay. So now the question is, should electricity be a 1 form or a 2 form? Okay. I mean, the electric field is a vector field, right? I mean, it comes from a force. A force in R3 has 3 components. So this is a question. Now, is there a good way to erase everything? Does anybody know?
I have no clue.
Yeah.
Also, Lauren, maybe the app that you were going to use was not like active, and that's why when you share the Zoom, it didn't appear.
Well, no. That
No?
app
Okay.
is always well, it's always here, and you know, like I have done Zoom hundreds of times this past year, and every time, no, it will show up. It actually doesn't have anything to do with the app.
Okay.
Really, whether I can show the screen or not. But you see, oh, you can see it, but I don't have that option to show us my screen. This is what I don't understand.
Yeah.
But anyway, right now we just use the whiteboard.
Whiteboard. Thank you.
Yeah. Okay, so the electric field E, okay, has 3 components. Let's say E1, E2, E3. Okay, so is it a 1 form or a 2 form? Because the vector field can be a 1 form or a 2 form. Now, I think it has to be a 1 form, and the reason is this. You know, in physics, you have this formula for work, right? So work is force times the displacement. So distance, basically, yeah. Force times distance. Okay, and that's when you have constant force and a straight line distance. But in general, work is the integral, you know, of electric force on a path. That's the work done on a path from one point to another. And because the path is one-dimensional, okay, you can only integrate a 1 form. And therefore, yeah, for this integral to be possible, force has to be a 1 form. So for this integral to be defined, force has to be a one form. Okay, you can integrate a one form on a one-dimensional object path, and you integrate a two form on a surface, you integrate a three form on a region in three space, right? That's what we learn in calculus, okay? Yeah. And so force is a one form, but since electric field is force divided by charge, a charge is a scalar, so a force is a one form. So this implies that the electric field is a one form. Okay. Yeah, and then so Maxwell's equation said, let's see, for electric field, says the curl no, let me see. What is that? Yeah. Right. So the curl of E, which is del cross E, is minus dB dt. Okay. Now let's translate it into differential forms. So the electric field is a one form, and I will call that one form omega of E. Okay. And so let's see. And then curl corresponds to D, right? As we said earlier. This is too faint. So curl of E would correspond to D of omega E. Okay. And then the magnetic field also corresponds to a form. Oh yeah, and here you see that the magnetic field actually has to be a two form, because D of omega E, that's a two form. D of a one form is a two form. And so on the other side, this is the time derivative of B. The magnetic field will correspond to a two form. Okay? So that you would have a two form is equal to a two form. And so this Maxwell equation would be, oh God, why does it become so thick? I don't know what I did. Oh, okay. Yeah. So this Maxwell's equation becomes D of this one form corresponding to the electricity is minus the time derivative of the two form corresponding to the magnetic field. Okay. Yeah. This would be Maxwell's equation in terms of differential forms. In terms of okay, yeah. And this shows also that the magnetic field has to be a two form. Mhm. This shows that the differential form of the magnetic field has to be a two form. Mhm. Okay. So we have written one Maxwell equation in terms of differential forms. And let me erase this so that I can write more. Okay. Yeah. Oh, maybe I'll leave that one there. Okay, that's one Maxwell's equation in terms of differential forms. You know, it's too bad that you can't use notability, because when I use notability, I can move equations around. Okay, now let's look at another Maxwell's equation. This time, the Maxwell equation for the magnetic field. Okay, so it's del dot B, okay? Okay, now you remember that del is ddx, ddy, ddz, as you learn in calculus. And let's say B is B1, B2, B3. Okay, so when you take the dot product, what you get is dB1 dx plus dB2 dy plus dB3 dz, right? And that's a definition of the divergence. And Maxwell's equation says that the divergence of the magnetic field is zero in a vacuum, okay? And now let's translate that into differential forms. So the divergence corresponds to D, the exterior derivative, and then the magnetic field corresponds to a two form, omega B, okay? And so this Maxwell's equation would just say that d omega B is zero, okay? In other words, omega B is what we said, closed. Yeah, so this is second Maxwell's equation in terms of differential forms. Okay, now the third Maxwell equation it says the divergence of the electric field, which is del dot E, is 0. Okay, now the divergence takes a vector field to a function. So in terms of differential forms, it takes D. It has to be D of a 2 form. So that it becomes a 3 form. And that 3 form is a function. And that function is 0. Okay. But you see that there is a problem here, right? Because what did we say an electric field is as a form? What kind of form is an electric field? Is it a 1 form or a 2 form? It's too bad I had erased everything, so I can't go back to the previous page. But do you remember whether an electric field is a 1 form or a 2 form?
A 1 form?
Yeah, it was a 1 form, right? Because we integrate force on a path. So force has to be a 1 form. So an electric field has to be a 1 form. But for this Maxwell's equation, we need an electric field to be a 2 form. So there seems to be a problem here. However, I said earlier that a vector field can be a 1 form or a 2 form, right? I wrote down that correspondence. So here, yeah. So what is the problem? Let me write that down. So since the divergence applies to a 2 form in R3. Divergence only applies to a 2 form. Okay. This E, the electric field, should be a 2 form. Okay. But there's a way to get a 2 form out of a 1 form. Should correspond to a 2 form. The electric field should correspond. But we said earlier that E is a 1 form. Okay. So that's because, well, we have this way of going from a 1 form to a 2 form and vice versa. Okay. So that is called the star operator. Okay. So let me tell you what the star operator is. Okay, so you see, you can always go from 3 form, 1 form to a 2 form, 2 to 1, and then 3 to 0 this way. So star of, say, the constant 1 is dx wedge dy wedge dz. Okay.
Sorry, there's like some noise. Maybe something is wrong with the microphone.
Oh,
Or right now it's nice, but when you were talking, like something was wrong with the microphone and there was some noise. But
really?
right now we hear you perfectly. So
Oh, right now it's okay.
yes.
Oh, I think earlier I was sort of pressing on my
Oh, okay.
computer. Maybe that's why I was pressing on the trackpad.
Yes. Okay. Great. Thank
All
you.
right, good. Thank you for telling me. And and then star of dx is dy wedge dz. Star of dy is dz wedge dx. Okay, it's cyclic. Okay, yzx, and star of dz is dx wedge dy. And then star of dx wedge dy. Now take a guess. What do you think this should be? It should be a 1 form. Who wants to take a guess? Which 1 form should I put down there?
DZ, maybe?
Very good. Yeah, it's always like the missing one. Okay. And then star of the dx dy, dy wedge dz is dx, and star of dz wedge dx is dy. And then star of dx wedge dy wedge dz. Okay, now what do you think that should be? It should be a 0 form, so a function. All right, it's 1. All right, so you have this star operator, and it can turn a 1 form to a 2 form and 2 form to a 1 form. Okay? And so this is how you can get a 2 form out of the electric field. And so like if E is the electric field, so omega of E is a 1 form, but star omega of E is a 2 form. Okay, so that's electric field as a 2 form. And then the Maxwell's equation, okay, for the divergence of E, it corresponds to, so okay, let me first write down the Maxwell's equation, right? So it says the divergence of E is 0, and this, okay, so the divergence is D of a 2 form, and that 2 form is star of omega E. Okay. Okay. And so this is the third Maxwell's equation. in terms of differential forms. And then the fourth Maxwell's equation is similar. So the fourth Maxwell's equation it says the curl of B is the time derivative of E. Okay. Now curl applies only to one form. But the magnetic field corresponds to a two form, as we said earlier. Okay. And yeah, so this Maxwell equation actually translates to D of, you need a two form, so it takes star of omega B. No, you need a one form. Okay, so and omega B is a two form, so you take its star, yeah. And then this should be the time derivative of the one form, omega E. Okay? Yeah. Okay, so this is how you write Maxwell's equations in terms of differential forms, all four of them. And now you see you can do electricity and magnetism, say on a three-dimensional torus, on an n-dimensional space, yeah, on any higher dimensional surface that we call a manifold, yeah. And this is how, in fact, physics is done, in well, I would say the second half of the 20th century and in the 21st century. Yeah. So Maxwell's equations have evolved. First it was written in terms of indices, then it was written in terms of vectors, and then now we write it in terms of differential forms. Okay. So this is a wonderful application of differential forms, and it's much easier to work with differential forms than with vectors because, for vector fields, you have the three different operations: gradient, curl, and divergence. But in terms of differential form, they're just one single operation. It's all D, just the exterior derivative, okay? Yeah. And that makes calculations much simpler. Okay, so I'm gonna end my talk here. Are there any questions?
Thank you very much, Lorena.
Okay, yeah. Well, it's nice to meet all of you. Let's see. Andre, Salvador, Daniel, Moise, Francisco, Lorena. Yeah. Pedro. Okay.
Actually, I have a question.
Yes.
The way you define the star operator here only work for three-dimensional, no? So
Oh.
how will we use this in n-dimensional space?
Yes, that's a very good question. And so, no, you can generalize it to any dimension. Okay, so let's see. Let's erase some of this stuff so that I have space to write. Yeah. So, you know, if let me see. Yeah. So if V is inner product space, that means it's a vector space on which there is a product. Like, okay, maybe I shouldn't do it so general. Yeah. So let's say if V is Rn with basis E1 to En. Oh, no. Well, let's see. We want differential forms. So with a basis of differential forms, with and you know, you actually want it to be like okay, let me just say, make it more specific. So with basis of differential forms, dx1 to dxn, to say that it's a basis means that you can write all the differential forms just in terms of these, right? Then star of dxi1 to dxik would be the other ones, okay? dxj1 to dxj, what is it? N minus k. However, with the sign, okay, so where the set J1 to Jn minus k is the set 1 to n minus I1 to Ik. So it's the other ones, okay? And then, the sign is plus it is plus or minus which, well, the sign is basically, it's the sign of the permutation. I1 to Ik, J1 to Jk. You see, let's do an example of this.
The J n minus k.
Oh, n minus k, yeah. J n minus. So let's say in R4, okay, you want to take star of, say, dx2 wedge dx4. So it should be the other one. So it would be dx1 wedge dx3. And then there might be a sign. So you look at 2, 4, 1, 3. Okay. What is the sign of this permutation? Now, the way you get the sign of a permutation is you look at how many inversions there are. Okay. This is an inversion. Oh, no, that's not an inversion. 2, 4, that's in the correct order, right? But 2, 1 is an inversion. That's an inversion because 1 is smaller than 2, okay? And what's another inversion? 4, 1 is an inversion. 4, 3 is an inversion. And there are no other inversions. So there are 3 inversions. And so the sign of this permutation is -1 to the 3, and it's -1. And so you have to put a -1 there. Okay. Yeah, you see, you need that sign because the wedge product is anti-commutative. So if you switch 3 and 1, then it would be a plus. Okay. Okay, Daniel raised his hand. Daniel, you have a question?
Yeah, I have a question. Is this star operator a sort of identification between the subspace that is generated by the K-forms with its orthogonal complement or something like that?
Yeah, you can put an inner product on the differential forms. And then this would be, this would go from, the subspace of differential forms. God, I erase it. Yeah, this would send a differential form to something that's orthogonal to it. Let me see. I erased something here. Oh gosh, when dx I1. But it's not an identification, right, of a subspace with the orthogonal complement because they don't have the same dimension, right? Let me see, do they have this? Oh yeah, they actually have the same dimension. Okay, you're right. So it takes the K-forms, the space of K-forms to the space of n minus K-forms. Yeah, right. It's a way of identifying the space of K-forms with its orthogonal complement. Yeah, you're right. Yeah. Yeah, so it works, in any dimension, this star operator. It actually works not just on Rn, but on any vector space on which there is an inner product, so that you can talk about orthogonality. Okay. All right, yeah. Any other questions?
Any more questions or comments for Dr. Tu?
Well, I hope I see you one day in person. I visited Colima in 2008, already 13 years ago. Yeah. And I love the city, wonderful with your 2 active volcanoes. And then I remembered that the seafood was really, really good in a town nearby by the sea. They catch the fish and then they serve it to us. Yeah, yeah. So one day I hope to visit Colima again.
You are welcome to come anytime. Just,
Yeah, right now we can't travel.
I know, but drop me a line and we will make
Yeah.
all the arrangements.
Okay, yeah.
And
All
now,
right.
it was a wonderful talk, but I was also surprised because it is the first time that you use whiteboard and everything worked well. I mean, you actually deliver it well. So thank you, Lauren.
Oh, yeah. Yeah, I never had to use whiteboard before. I thought I couldn't use it with my Apple Pencil, but it turned out that I could. So that makes a huge difference.
Yes, yes, it was great.
Yeah.
Of course, it has a lot of limitations. You cannot scroll down.
Yeah, I cannot scroll up and down, and I have to erase what I had written. You know, the big advantage of using other apps like Notability is that, you know, then at the end of the lecture, you have a written transcript.
Yes.
And so I post that written transcript, you know, for every lecture that I give. And that way the student or the audience can go back and see what I said. Yeah. Yeah.
Yes.
But yeah, I don't understand why it didn't work this time. This is the first time in the hundreds of times that I have used Zoom where I couldn't share my screen.
Well, not because you are in Mexico. Different laws.
Yes, I don't know. Yeah. Yeah.
So, final call for the students or any comments or questions for Lauren.
Oh, normally are your classes in English or in Spanish?
Right. The first 2 years, they are in Spanish. And the last 2 years, they are taught in English.
Oh, okay. So you see, I was a little bit surprised that the students who ask questions in English,
Right.
you know, speak English so well. Yeah.
No, thank you for mentioning that to them, especially they need to hear that.
Yeah, it's true. I didn't notice any difference, you know, when I teach my American students. Yeah. Yeah.
And also, as I mentioned, Pedro and Francisco, they are so 4th semester students, but you already saw Francisco ask you a question, and it is also because by this time they have already covered multivariable calculus. So your lecture was suited for them very well.
Okay, okay, that's great. That's great to hear. Yeah. All right, so thank you for attending the lecture. Hope to see you again in person, maybe. Yeah. Okay. So I guess I will leave now, right? Yeah.
Right. Thank you very much, Lauren.
Okay.
And also let me know if the video will be there on YouTube. If you want me to erase it, just let me know and I will take it.
No, that's fine. You can post the video.
Thank you.
Yeah.
I truly appreciate it, Lauren.
Okay, great. Yeah. Okay, so take care, everybody. And I will be leaving now. Bye.
Adios.
Adieu.